Hey everyone. So today my topic is about Lewis structures, and it's fairly simple, and hopefully I'll be able to portray it in a way that makes sense. Definitely not perfect and a pro at chemistry, but we will see how this goes. So what is it? So a Lewis structure is a two-dimensional representation of a compound showing how its atoms are connected. So to put it in simple terms, it just displays how different atoms are connected and shows their bonds and valence electrons. For people like me, how I feel like sometimes in different science classes, it's hard to kind of grasp ideas or picture how something is in something like chemistry because it can be so microscopic. Um, Something like this helps, like Lewis structures, because I can draw out what this structure looks like and see how it can react with itself or other structures and kind of get a better idea of what it is and its relativity to everything else. To first talk about Lewis structures, let's break it down a little bit more and talk about Lewis symbols. Not sure if you guys can see my little picture, but we'll move that out of the way. So Lewis symbols. So they display the bonding capacity for an element or the number of valence electrons a given element has. So it is just a little representation or image of each of these elements and what exactly, or how many valence electrons they have, basically. And with how many valence electrons it has, that shows us how many places it has where it can have a covalent bond. Yeah, so it shows the bonding capacity. And so we can know it just by looking at the periodic table. So it goes by the different families or columns to know how many electrons are in each one, valence electrons. So we have like one has one, and then two has two, and then we skip this area, and then we start back at 13, and we go with three, and then four, and then five, and then six, and seven, and eight, except for but anyways, so if we know that, then that will help a lot with making Lewis structures because we will use these to know how many valence electrons and to in turn know just how many bonds or extra um, valence electrons it has. Yeah, so we can look at some examples of these Lewis symbols real quick. Okay, there we go. That was weird. So here we have carbon. So the scene right here. So if we want to know how many valence electrons it has, we can look at our periodic table. And so if we know where it's 1, 2, 3, and 4, so we know that I'll have 4 valence electrons. And so now, what do these valence electrons mean? So because there are 4 valence electrons and they're each separate and not paired, this means that they will, there's 4 places where the carbon can bond with other elements or atoms. And so it means that there are four possible places that can have covalent bonds because there are 4 individual valence electrons here. So if we look at another example, if we think about nitrogen, yeah, let's do nitrogen. So we go 1, 2, and then 3. So it's 4 and 5. So it has 5 valence electrons this time. So it's a little bit different than carbon, where we've talked about so far. And this changes things a little bit because whenever you are listing these valence electrons, you go, it doesn't matter what order you do it in, but you have to fill in the 4 spots first. So for the 1, 2, and 3, it doesn't matter where they are. It's just 1, 2, and 3, and then 4, it's 4, so it can't go anywhere else. But whenever you get to 5, 6, or 7, or 8, then you have to start pairing electrons. And so, for example, on carbon, you can't just put electron here and then add this one to it and have it paired. You just can't do that. And so we have the 4 electrons, 1, 2, 3, 4, and then there's a 5th one, so we have to pair that with another one. And because because this electron is already paired, that means that it will not be able to pair with something else, which is fairly simple and easy to remember. And so if that one's already paired, that would leave 1, 2, 3 places where it can pair with something else. And so there are 3 possible places that nitrogen can have covalent bonds. So let's do an example of drawing a Lewis structure now. I can kind of explain how to do it as we go. So here we have CH4, which is methane. So let's take our carbon and our hydrogen. And there's 4 hydrogens, but I just have 1 here. So carbon, as we discussed, has 4 points or areas where it can bond of covalent bonds, as it has these 4 different valence electrons. And we have 4 hydrogens. And so these 4 hydrogens will each connect to one of these valence electrons of carbon. And so whenever you have 2 electrons or 2 of these dots connected or going together, it forms a line. And so anytime we have a line, this signifies that there are 2 electrons. So to put it all together, as said, we put the hydrogen here, 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 and here, which makes this. And so as I also said, these lines mean 2 electrons. And so there's electron from this hydrogen and electron from this carbon, then this hydrogen and this carbon, and so on. So this is a fairly simple Lewis structure and a good example to start with to see kind of how it works and how you form it and what it is exactly. So covering up stuff. So let's do another example. A little bigger one now, or some more electrons. So draws Lewis, and so these are from the practice or the recitation problem sets. And so I just grabbed some questions from there so we can look at it simply, and you can, it makes it easier for you to go back and look at it also if you want to look through it again. So we're drawing a Lewis structure for, no idea how to say that, but it is COCl2. A poisonous gas in chemical warfare during World War I warfare. So we take our individual elements, and so we have carbon, oxygen, and then chlorine and chlorine. And so now let's think about, there we go, back to this, of where this carbon, oxygen, chlorine. And so if you have a periodic table with you, you can look at it, and you can see that carbon has 4 valence electrons, and oxygen has 6, and then chlorine has 7, as seen here. And so now that we know how many valence electrons all these are, now we need to form it into a shape, but we have 4. And so how do we know what is going to be the central atom in this structure? So the way to know this is whichever one has the least amount of electronegativity. I'm like decently drawing a blank, but I believe that's correct. Sorry if it is not, but I believe it is. And so the higher electronegativity increases as it goes to the right on the periodic table and up. And so if we look at, or I remember already, so if it's CO and Cl, then the least electronegative atom will be, or element will be carbon, because it is, as I said, electronegativity goes up, increases as we go to the right and up. So up here will be more, and then here will be less than both of those. So with that, we can know that carbon is going to be the central atom. And so once we have carbon as the central atom here, we can reform the other elements around this carbon to look like this. And now we need to add everything else. So we know that carbon has 4 valence electrons, oxygen has 6, and chlorine has 7. So we can start with this chlorine. And so we'll have 1 bond here, and then there's 7 electrons total. And so there'll be this bond already. So there's 1, and then 2, 3, and 4, 5, and 6, 7. So perfect. This chlorine is done. We've already used all 7 of the electrons, so we don't need to worry about that. And it'll be the exact same for the other chlorine. And so we'll have another electron right here connecting to this, which will make a bond, a line, where we will have the 1, 2, 3, 4, 5, 6, 7 electrons. Now for the oxygen, oxygen has 6 valence electrons. And so the carbon will have a bond there, and the oxygen needs 6. So I'll have 1, 2, 3, and 4, but there's an extra. And so this is where we will have what's called double bonds or triple bonds. And so because the carbon is using 3 of the electrons, but it has a free valence electron that is not connected to anything, we will, and also the oxygen doesn't. And so whenever there's 2 elements or atoms that do not have, or that do have a valence electron that's not connected to anything, those will connect to each other and form another bond. And so in this scenario, we will have a double bond here between the oxygen and carbon, and leaving 2 valence electrons. So as seen here, we have there would have been a extra carbon and an extra oxygen valence electron, and those 2 form to connect a second bond, which is a double bond. So nice. So let's do another example, Ammonia Nh3. And so the nitrogen has 5 valence electrons, and then all these hydrogens have 1. And so we have 5 and then all 1. And with this, what will be the central atom? So although it may appear the hydrogen would be it because it's all the way on the left side of the table, this is not true in this scenario because hydrogen will not be hydrogen won't be a central atom in a Lewis structure. It just can't be and won't be. So we already know that nitrogen is the central atom. So we can form those hydrogens around that. And so each of these hydrogens just have 1 valence electron, and nitrogen has 5. And so we have 1 here, 1 here, 1 here, then the hydrogen will connect, and the hydrogen will connect, this one will connect. But there's 2 extra valence electrons for nitrogen. But as we discussed, whenever there are 2, they're a pair. And so they're already done. So we don't need to do anything for them. And so this will lead to nitrogen having a pair with it. So not a lone pair, but, or yeah, it'll have a pair with it. And so there's the hydrogen, and then the nitrogen with the pair here. And so those don't form bonds because hydrogen can't, only has 1. So that'll just form its own pair right there. So that's all it is. Now let's do monochloramine. So we have 5 valence electrons for the nitrogen, 1 for hydrogen, 1 for hydrogen, and then 7 for chlorine. And so I guess we didn't add middle stuff, but we can just walk through it. So nitrogen will have 5, as I said, and that will be the central atom. And so as there's the nitrogen, there will be the hydrogen, and then the hydrogen around it. I guess we can just look at it. So because there's 5 for the nitrogen, there's going to be the 1 bond to the hydrogen, 1 bond to this hydrogen, and then 1 bond to the chlorine, leaving 2. And so the same deal as ammonia, yeah, where there'll be this pair right here. And so that'll be the extra pair, and then it'll connect to the chlorine, which has 7. And so there's the 1 electron right here, because whenever there's a line, that means there's 2 electrons. So there's an electron from chlorine and an electron from nitrogen. And then we have the rest of the valence electrons, which will be the 2, 4, and then 6, and totaling up to 7. And so that's all it is for that. So now let's talk about resonance structures a little bit. So resonance structures. So what is it? So resonance structures are when two or more equivalent Lewis structures can be drawn for one compound. And so there's different scenarios like we talked about where there is a double bond, for instance, or actually, no, that one you can't do it. We will just not talk about that example. Talk about this example, ozone. So ozone is O3. So there's 3 oxygens. And this is up in the sky, as we know, like the ozone. But so whenever you build this structure, there is so whenever you build it, we have the 3 oxygens and the pairs and then the bonds. But the thing where this is different now and where resonance structures come into play, where there's 2 or more equivalent like Lewis structures, it's because we could have this bond here, but it can also be over on the other side as well. So as seen here, this is a resonance structure for ozone or O3. And that's because the double bond could also be on the other oxygen on the other side. And so fairly simple there. So yeah, now let's talk about bond order. So bond order, not sure if I have an explanation. No, I don't. So bond order is where you just take how many bonds are in a structure. And so, but even though, and so if this was NO, but with only one, if there wasn't a double bond, so if there were only single bonds, then it would be that number. So there's 2 bonds, and so that's how many bonds there are. But in this one, nitrite ion, there is a double bond here and then a single bond here. And so there are 3 total bonds. So there's the 1 bond here, 1 bond here, because it's a double bond, so it's 2. And then the single bond, so it's 3. And so since there are 3 bonds, that is divided by how many like places there are bonds, I guess. Sorry, I was, never mind. And so we have the place here and here, so it's 2. So we do 3 divided by 2 is 1.5. And so the bond order for nitrite ion is 1.5. And so this is also an example of a resonance structure as well, because it's somewhat the same example as this, where it'd be the same if you flipped it or had it on the other side. And so we have the double bond on this right side, and then this extra. We have this here, and then the double on here. And so those can also be flipped, so that this would be on the other oxygen, and then the double bond would be on the other oxygen, with shown by these arrows that this is a resonance structure. And then, yeah, bond order 1.5. And so now for a quick explanation of ionic compounds, and just a quick example I have right here. It's only about a minute.
After making a free account, I can go ahead and pick the subject that I want to learn. As you can see, there's a...
But also elements in the 3rd row of the periodic table and below often have more than 8 valence electrons. Beryllium and boron are no thing, is really more of... Let's say I want to draw the Lewis structure for sodium chloride. Sodium has 1 valence electron and chlorine has 7. Since sodium is a metal, this must mean that it's going to be an ionic bond, meaning that electrons are transferred. Sodium transfers its 1 valence electron to chlorine, creating a +1 charge on the sodium and a -1 charge on the chlorine. The 2 ions are attracted to each other due to their opposite charges. They're written slightly separated because the electrons aren't shared, but they're not too far apart because the ions stay close enough together to neutralize their charges. Lewis structures use a line to denote covalent bonds, but we're not doing that here because there are no covalent bonds. It's an ionic bond, and there's no physical contact between the ions. So that is what salt looks like from a Lewis dot structure point of view. Covalent bonds, a little more complicated, and it works best if you follow some specific steps. Let's try it out with water.
All right, we already talked about that. So I hope that audio worked. That should be the last one. Yeah. So that's a quick example of ionic compounds. Focus most of the time on the structures. But anyways, I hope that all made sense. Just the basic idea that Lewis structures are showing how different elements form together and how they're bonded. So just here where we have the lines connecting the valence electrons. And overall, if you have this chart known, and it's pretty simple to be able to look at a periodic table and just remember that, like 1, 2, 3, 4, 5, 6, 7, 8. It took me a little bit, but I eventually realized that 13, or like the 3 matches up the 4 or 5, and that helps make it a little bit more simple as well. But yeah, so Lewis structures, you do this. These are the Lewis symbols first off, and then the Lewis structures, you just build it and use the valence electrons and use all of them. You can't just have, for example, in this, you can't just be missing a pair of here. So you need to be really careful with counting and making sure your numbers are correct. That's one of the difficult things with Lewis structures, is just very tedious and intricate of how you need to make sure to remember all the numbers, and or not remember them, but just remember to list them all. So you make sure to show and display all of the valence electrons and then all the bonds. And then remembering that I should have had an example of a triple bond, but for example, here where there's the double bond, where whenever there's an extra electron, an extra valence electron, those two will connect. And then resonance structures where they can flip, have different versions of themselves, basically, of the same compound, where just little things different, like bonds flipping in the bond order. You just do that by how many bonds. There's 3, and then how many areas where it's bonded. And it's 2, so that'd be 1.5. Then the and so that should cover 4.4 through 4.6. I know I didn't go through everything specifically, but I grabbed most of the resources from the textbook or the problem sets. And so if you have any questions about any of the parts, take a look there, and those should have go much further in depth and have other examples and ideas, because the problem sets are really good for these ones. They have really good repetitive questions that will help you practice it more and really get it down better. And yeah, that's pretty much it. I hope that all made sense, and good luck on the test. Hope you all do well.